Welcome students to the VTU EduSat program on automata theory and computability. Let us continue with the lecture 10 with regular expressions. Myself Girijamma HA, I am working as a professor in the department of CSC RNS Institute of Technology. So you can, for any queries, you can reach me at the displayed mail ID. So let us continue with the today's topics. So today first we will be discussing the equivalence of regular expressions and finite state machines. So this already we have proved in the Kleen's theorem in the lecture 8 and lecture 9. So we will focus on that expressions. Next is writing the regular expressions. Sometimes regular expressions will not be so easy, they will be very complicated. So we will write how to write the regular expressions in those cases. Next is building a DFSM, that is deterministic finite state machine. Next topic we will be discussing is about the algorithm build keyword finite state machine. Next we will be continuing with the example on the above build keyword finite state machine. So next topic will be applications of regular expressions. Next, regular expressions will be writing especially for decimal numbers, legal passwords and IP addresses which will be using in computer science. So next is manipulating and simplifying the regular expressions. So next, so this is the end of the regular expressions. So we will be discussing some exercise problems how to go ahead with. Okay. So first is, let us see the equivalence of regular expressions and finite state machines. Okay. So we know that we have discussed it in the lecture 8 and lecture 9. So for any regular expression there exists an equivalent finite state machine. Okay. So this we have done, we have proved it using the construction method. Okay. So this is the Kleen's theorem statement. So what does it say is the class of languages that can be defined with regular expression is exactly the class of regular languages. So we know that from the module 1, so if an finite state machine either DFSM or NFSM, if it is accepted, then we say it is regular. Okay. So this regular expression, so this we have proved in the lecture 8. Okay. So what does it says is, theorem 1 says that every language that can be defined with a regular expression is regular, and theorem 2 says that every regular language can be defined by the same regular expression. That means, so this we proved in the previous class by taking the finite state machines as examples. Okay. So we solved some 5 to 6 problems and we discussed the 2 algorithms, that is the heuristic and another one is standardize and build regular expression. Okay. So using those 2 algorithms, so we constructed the regular expression using a finite state machine. So these 2 are proved. So now let us focus on how they are affected. For example, so when we want to write the regular expression, okay, so for let the language be there is no more than one B. So this question already we have discussed in the module 1. Okay. So for that you have a DFSM like this. Okay. So this is, it is having 3 states Q0. Okay. So for example, so Q0 is the start state and starting it can have any number of A's followed by single B, it reaches the final state. Okay. Afterwards only one B is allowed, it can have any number of A's, so it can be defined in a self loop, and after this if it is accepting any regular expression or any transition with B, it is going to reach a dead state. Okay. So why? Because the language here is given is there is no more than one B. Okay. So there is no more than one B means, for example, if you write the strings of this language, so it can be epsilon. So starting only Q0 is also a final state, so it is accepted. Next single B, so with Q0 with single B it reaches the state Q1. Next single A, so single A it reaches it will be in Q naught itself, so it is accepted. Next AA, again it will be in self loop, so like that it will be in Q naught. Q naught is also one of the accepting state. Next AB, okay. So single A followed with B, it reaches Q1. Q1 is also a accepting state, hence this string is accepted. Next BA, so starting B from Q naught. Next A, it will be in self loop, so it is accepted. And similarly you can test all the strings. For example, ABA, it is in Q1, BAA, that is BAA. So all these strings, they contain 1 B, so they will be either in Q naught or in Q1, okay. So if there are no B, if there are more number of B's, then we are diverting to dead state, okay. So dead state is the state you can reach the dead state, but there is no way to come out from the dead state. So for this, if you want to write the regular expression will be A star followed by either B or union, okay. So why we have taken here epsilon is, okay, so either sometimes only A can be there, likewise here in this string only A is there, AA is there. So either B or epsilon, again followed by, it can have any number of A's, okay. So this will be the regular expression. It is A star followed by B union epsilon followed by A star, and so the FSM will look like this. So let us proceed further. This example also we took in the module 1 and we constructed the FSM like this, okay. So actually there is a print mistake in the textbook. This should have been a dead state, but he has made it a accepting state, so you can make the correction of it, okay. So actually it is not an accepting state, it is a dead state. So what does the here the problem is, so L is defined as a strings which contain AB star such that no consecutive letters are same. No consecutive letters are same means in the strings there should not be AA, BB, like that continuous same symbol should not be repeated. So if you write the language, it contains epsilon, A, B, AB, BA, ABA, BAB, AB, ABA. So if you observe, there is no continuous AA or BB. And if you construct the FSM, so FSM, so starting in Q naught, it can accept either A or B, okay. So if it accepts A, then it reaches Q1. If it accepts B, then it reaches Q2, okay. So there can be single A, B also. So that's why we have made Q1 and Q2 as accepting states, and then after Q naught, after accepting B, again it cannot have B, so it should contain A. Suppose if it contains B, then it reaches a dead state D, okay. So here in a similar way, A followed by, it should contain B only, there cannot be AA, okay. So continuous A's or B's are not allowed, so that's why here there are no self loops on these 3 states, okay. So if you observe Q naught, Q1, Q2, there are no self loops. So if you write a self loop, it can accept more than 1 A's, and even here if I write like A or B, it can accept more than that, okay. So after A, if it is either A or B, it reaches the dead state. And what about the regular expression? So regular expression will be B union epsilon, okay. So first I am taking this one, followed by A, B whole star, that means it can have any number of A's followed with B, okay. So that's why first B or epsilon, okay. So or A, B followed any number of times, that's why it is having star mark, followed by A union epsilon, okay. So followed by A, so it reaches the state Q1, okay. So either it can end in Q2 or Q1 or Q naught, or so this is one possible way of writing the regular expression. Or also it can have like starting, it can have A then or epsilon followed with B A star. So that means here B A, it can be repeated any number of times. So that's why I have written here A union epsilon followed with B A whole star followed with single b or epsilon, so it reaches the final state. So either you can write this way or this way, both are possible because the strings contain starting either A or B. So this is of no two consecutive letters are same. This DFSM, that is the deterministic finite state machine, so we have constructed in the module 1. Next is we will write the regular expression for floating point numbers. Okay. So floating point numbers, so it contains starting either plus or minus followed with epsilon. Okay. It may not contain some numbers also, followed with any numbers, then followed with an optional dot, and followed with again digits, then followed by e. So followed with plus or minus or epsilon, and it contains some digits. Okay. So this is the format of a floating point number, and we constructed an equivalent DFSM, that is deterministic finite state machine, like this. So how does it includes? So starting state, it can have plus or minus, then followed with any number of digits, or without this also it can have digits. It will reach the final state with only numbers. Okay. So or else it may be followed with dot. Okay. So dot followed with some digits, then followed with e, then followed with plus or minus. So after e, without plus or minus also it can have only digits. So that's why this here, this is possible, or here it may not have dot, but it may have he. So that's why all options are given in this DFSM, and then it will reach the final states. Okay. So there are 3 final states here, and examples of this string are 24.06, or it can have sign here, sign after this e. So and then we can write out many examples. Okay. So if you look at the regular expression for this, okay, so it is similar to how you constructed the FSM. Similarly, starting you can have either epsilon or plus or minus. Okay. So when there are 3 options, so you can combine with union. Okay. So that's why starting you can have either epsilon, union plus, or union minus, followed with d plus. So what does d plus says? It is one or more times repetition of d. So what is d? D is nothing but a digit, and it can be either 0, 1, 2, 3 up to 9 digits. Okay. So it can have starting plus or minus, followed by one or more digits, then followed by dot. Okay. So dot is not compulsory. So that's why even you can include epsilon or dot, followed by d plus. Okay. So again d plus means one or more times of digits repeating, followed by epsilon. So either exponential part may be there or may not be there. So that's why we have written here epsilon. If it is not there, if it is there, then e, followed with again it can have plus or minus, followed with digits. Okay. So this is the regular expression for floating point numbers, and this is the FSM for floating point number. Next we will see the building of DFSM. How to build the DFSM, deterministic finite state machine. Okay. So it is possible to construct the DFSM directly from the set of patterns. Okay. Suppose we are given a set of n keywords and the text string s. Okay. So we have to search for text string s from the keywords. Okay. So find the occurrences of s in keywords k, and k can be defined by the regular expression sigma star. Okay. It may contain any of these strings, followed by, so set of keywords are defined with k1 union k2 union up to kn, again followed by sigma star, and this can be repeated one or more number of times. Okay. So k is nothing but a set of keywords, so which can be defined with the regular expression. Now, so we are searching the occurrences of s in this set of keywords. That's why, so accept any string in which at least one keyword occurs, and this is the algorithm build keyword FSM. Okay. So, what does it says? To build deterministic finite state machine that accepts any string with at least one of the specified keywords. So, this is the algorithm build keyword which contains the set of keywords. So, for that we will how to create that set of keywords. Okay. So, first we will start with a key knot, then for each element that is for each element keyword so of k, so we will create a branch corresponding to the k. That's what, suppose if it is cat, bat, like that, just we will go on adding the steps, and we will make the last symbol to be accepted as a final state. Next, we will create a set of transitions that describe what to do when the branch dies. So, this is very important, and this part we have not constructed till now. Okay. So, what does it says? Create a set of transitions that describe what to do when a branch dies. That means, suppose if you are searching for a cat in a cat keyword, suppose if C is not present in that state, then what to do? So, you should specify it. Then make the states at the end of each branch accepting. So, that normally we will do it after after accepting the each word. So, last state will be the final state or the accepting states. Okay. So, here the new part is this thing, that is we should define the transitions for each state whenever a branch dies. So, this is the algorithm build keyword FSM. So, let us see this algorithm by using an example. For example, in our database the keywords are cat, bat and cab. Okay. So, if you start with Q naught, so according to the algorithm what he says, for each symbol create one state and then define the transition. So, starting with C, A, T, it reaches the final state, and afterwards any character, so it will be in the accepting state. And similarly we have to define for cab and bat. Okay. So, this is the transition for bat, B-A-T. Okay. So, starting state Q naught, B, then A, T, and similarly for cab the third example C, A, B and reaches the final state. So, here suppose let me say, for example, after C again I have cat, or after A I have cat. So, here we have not specified what to do. So, that is why for each transition we should define what we should do when a branch dies. Okay. So, for this, so you can define the transitions like this. Okay. So, for example, if it is from the Q naught you are defined for C, then you are defined for B. Other than that, what it should do? Not of B and C means other than C or B, it will be in the same state Q naught, and once if C is found, it reaches the next state. Okay. So, here again with C, after C you may have again C, then A followed with T. Okay. And here also you can have B. Okay. After C in your database you may contain bat. Okay. So, likewise from the C directly you can define B here, and you have defined A, C you have defined. For all others, so you can define not of CBA, it can reach to Q naught. That means, so here, so what in while searching, so in each state, so suppose if the word is not found, it may be found further, so it will goes to some other state, and whenever it is found, it reaches the final state. So, like that, so we have defined for all the states. So, if you observe here, T is defined, B is defined, and then C is defined. So, not of TBC we have given for Q naught, and similarly if you find this state, so self loop B is defined, and again A is defined, C is defined. For all other states it reaches the Q naught, and similarly all states, so you should define like this. That means, so this is a proper way of the building the DFSM. So, like this, for any set of keywords. So you can maintain the database by constructing the DFSM like this, so that whenever you are searching the keyword, okay, so actually this comes in the compiler design. The first phase of the compiler design is the lexical analysis. So the output of the lexical analysis is a token. So there you have to match either it is a keyword or a floating point number. So in your database, in your compiler design, so it will be stored in an finite automata like this. All the keywords will be stored, and whenever you are searching the keyword, so it will be searched, and if it is found, it reaches the accepting state. This is one application and also an example for building the deterministic finite state machine. Okay, so let us move to the applications of regular expressions. So till now, so we have seen how to write the regular expression, how to write the finite state machine from the regular expression, and how to construct the finite state machine from the regular expression, and regular expressions from the finite state machines. Okay. So where these regular expressions are used? Regular expressions, they are used in scripting languages, and they provide for regular expression matching. So if you are working with Perl, then if you are working with Perl, so there will be using the regular expression. And in our daily mailbox, so how your spam mails are entered in spam folder? So by using the regular expression. Okay. So for example, some advertisers, they will be using some keywords. So those are all matched with the spam messages, and they are filtered to the spam folder. So likewise, you can filter any of the mails to the particular folder. For example, so in the staff, suppose if we are collecting the question papers, so these question papers, they can be moved to the question paper folder. You can create one folder question paper, and if any staff, if they are mailing the question paper, so those can be moved to the folder. So likewise, you can create the regular expression, and it can be used as a project. And in the biological field, it is useful in the words protein sequences. They are called as motifs. And as I said, they are used in the lexical analysis. So lexical analysis, it is the first phase of the compiler design. Okay. So lexical analysis, what it will do is, it will return the tokens. Okay. So it will accept the C language or whatever the programming languages you are written it. Okay. And it should identify and return as a token. Okay. So these tokens, so they are matched with the database. So likewise, as we have seen in the previous example, so you can have a DFSM as a for the set of keywords, and suppose if you are matching the keywords, then it can be used. And also in web, you can find the patterns. Okay. So patterns are nothing but strings, and whenever strings we are using, we can use the regular expressions. And lastly, so to create the legal passwords. So you know, different passwords, they will be having some rules. Okay. So again, we will further discuss how to write the passwords for how to write the regular expressions for passwords. And also regular expressions, they are used in variety of text processing tasks, and they are used in string processing where data need not be textual. And common applications of regular expressions, they include in data validation, data scraping, mainly in web scraping, data wrangling, simple parsing, as we saw in the lexical analysis, and in the production of syntax highlighting systems, and many other tasks. So these are some of the very important applications of regular expressions. Next, let us write some more regular expressions for decimal numbers. Okay. So here this IE matches the decimal encoding of numbers. Okay. So here we will use a notation which is alpha. Alpha is any regular expression What do you mean by question mark? Okay. So, in a regular expression which is followed by question mark means 0 or 1 time repeated. Okay. So, means that a regular expression alpha can occur 0 or 1 time. Star means the regular expression alpha can repeat 0 or more times. Okay. So, you should remember question mark means it is 0 or 1 time and star means 0 or more time. And similarly alpha plus means the regular expression alpha, it can repeat 1 or more times. Okay. So, using this concept, so we have written the regular expression for decimal number. So, decimal number, so either it can have minus, so this minus can be either, it cannot, if it is a plus number then we will not be using it. Okay. So, it is 0 or 1 time repeating and then followed with any numbers. So, this is 0 to 9 plus, that means this can be repeated 1 or more times. Okay. So, after here minus, one number should be there compulsory, followed by dot. This is the escape sequence for dot. Okay. So, we are next followed with 0 to 9 star. Okay. So, that means it can have 0 or more number of digits. So, this whole this in question mark, that means, so in a decimal number only 1 time dot will occur, or you cannot have, if it is an integer only 24 like that, then it dot will not be there. So, that is why if dot is there then either it is 0 or 1 time, or it can also have dot followed with digits, that is 0 to 9 plus. Okay. So, either this or this. So, anything. So, this is the regular expression for decimal numbers. So, it may vary here. Sometimes we will be using plus, but plus is not used. So, even like floating point numbers, how we are used union. So, like that here also while writing the regular expression for decimal numbers, so we can use that also. So, these are some of the examples. So, using this regular expression, so I have written here. So, it is 24 or 0.23 or minus 24. So, these are some of the examples. So, next let us write the password. Okay. So, what is a legal password? So, every system it will be having some rules. Okay. So, like a password must begin with a letter, then it should contain letters or numbers, then and it can also contain underscore character. Okay. So, starting it should begin with a letter, followed by it may contain letters or numbers or an underscore character, and then it should contain at least 4 characters and maximum of 8 characters, not more than 8 characters. Okay. So, if you try to write the regular expression for this, so it looks like this. So, starting it can have either capital A to Z, small a to Z or caps A to Z, followed with A to Z or numbers or underscore. Okay. So, likewise, so it can have any of these 3. For this remaining 3 it is compulsory. Okay. So, that is why epsilon is not there. Okay. Then it can contain epsilon. Why here epsilon? Because minimum 4 letters should be there for a password. Afterwards it can be either 5 or 6 or 7 or 8. Okay. So, if you there is no line breaks here. Okay. So, continuously if you write the regular expression, so you will be getting a very lengthy regular expression. Okay. Very lengthy and very complicated regular expression, and once if you see, you will not understand what is this. Okay. So, right now I have explained what is this, you know it. How to simplify this regular expression? Writing this regular expression. Okay. So, here, so we are using a different notation for writing the regular expression. So, we know that alpha means it is a regular expression or the pattern, and that must occur exactly once. Alpha star means the pattern may occur any number of times including 0, and alpha plus means the pattern alpha must occur at least once. That means, so it can occur more than once also, but at least once it should contain, and this is a different notation we will be using it. Alpha in a flower bracket followed with nm means that the pattern must occur at least n times but not more than m times. Okay. So, we were writing for the password. So, it should contain minimum 4 times, not more than 8 times. So, in order to include those options, so here regular expression can also be written as alpha of n comma m, means that the pattern must occur at least n times but not more than m times. And similarly, so suppose sometimes we want to write exactly. Okay. So, that time we can use alpha followed by n, means that the pattern must occur n times exactly. Okay. So, using these notations, let us write the password for a legal password. Okay. So, legal password, first it should contain either a small letter A to Z or capital A to Z. Okay. So, then followed by either AZ, or it can be digit, or it can be underscore, and here this can be minimum 3 times compulsory. Why this is? Because legal password, it should contain 4 letters. So, that is why, so starting this is compulsory, because every password it should start with a letter, then followed with letter or digit or an underscore, and this should be minimum 3 times and a maximum of 7 times. That means your password length totally it will be 8, of which first one is fixed. So, remaining 7, so you can write 3 comma 7. So, instead of writing such a lengthy password, so you can cut down and you can minimize and you can write like this. So, that is first letter followed with letter or digit or an underscore, and this can be repeated minimum 3 times or maximum 7 times. For example, so if you write like this here RNSIT underscore 17. Okay. So, this is an example of a legal password. Likewise, I have written all the letters, no problem, because only starting is specifying and afterwards it can have all the 7 as letters only. So, that is why I have written all as letters, or it can be VTU underscore 2007. So, like this. So, you can write the password and this will be the regular expression. Similarly, let us write the regular expression for an IP address. So, what is an IP address? So, IP address is the system's location where it is located. So, you can get through the IP address. Okay. So, IP address it follows first contains some digits 0 to 9. So, here 1 comma 3. What does it means? That means this at least one digit should be there and maximum 3 digits it can have. Okay. So, followed by dot, again followed with 0 to 9, 1 to 3. That means after the dot it can be 3 digits maximum. It can be less than 3 also, but maximum it can have 3 digits, and this whole thing it can be repeated 3. That means in an IP address, so you can have only 3 digits, 3 dots. Okay. So, you can have 3 points like this. So, this is the way of writing the IP address. Okay. So, starting it can have number and this is can be repeated 1 time or maximum 3 times, followed by dot. This is the escape sequence for dot, followed by numbers. This is 1 comma 3. That means, so either you can write 121.12 and then you can stop. Okay. And this can be repeated maximum of 3. Okay. So, here I have written maximum 3 and afterwards again it cannot have the dot. If you see any IP address, only you will be finding the 3 dots. Similarly, so we can write 118.102.248. So, maximum 3 and 3 digits. And similarly, here 10.1.23.45. Okay. So, here 3 points are there and it can be either 3 or less than that, but not more than 3. So, this is how you can write a regular expression when the things are complicated. So, till now, so we have seen the regular expression. Let us see how to manipulate and simplify the regular expressions. So, let alpha, beta, gamma represent the regular expressions, and we have the following identities. So, what all the identities? So, identities involving union, and we have the identities involving concatenation and identities involving the clean star. So, these three, why only these three? Because these three are the operations we will be using in the regular expressions. So, let us see one by one. So, first is identities involving the union. Okay. So, union is commutative. So, alpha union beta is beta union alpha. So, and next similarly union is associative. What are all this alpha, beta, gamma? They are any regular expressions. Okay. So, likewise union is associative. That means alpha union beta followed with union gamma. It can also be written as alpha union beta union gamma, and phi is the identity for union. Okay. So, if you perform phi union any regular expression, it will be the same regular expression. And similarly union is idempotent, that is if you perform the union of the same regular expression, it will be the same regular expression. And similarly for any two sets A and B, suppose if B is a subset of A, then A union B is nothing but A, because B is a subset of A. Okay. Similarly the same concept here, it is used in union. Suppose you are performing A star union AA, it is nothing but A star. Why? Because the language of AA, it is a subset of A star. Okay. So, you can from this language you can derive this AA. So, that is why AA will always be a subset of A star. So, you in these cases, so you can rewrite and you can simplify the regular expression and then write as A star. So, next we will be using all these identities for simplifying the regular expressions, and similarly we have the identities involving concatenation. Okay. So, concatenation is associative, like alpha beta into gamma is nothing but alpha followed by beta gamma, and whereas the union phi is the identity for union, whereas here epsilon is the identity for concatenation. That means, so whenever you have epsilon, whenever you have alpha followed by epsilon, it is nothing but alpha, and phi is 0 for concatenation. So, whenever you are performing the concatenation with phi, it will always be phi, and concatenates, distributes over the union. Okay. So, these are the expressions. Suppose if you have union and concatenation together like this, then so while maths how we write, in a similar way you can perform alpha gamma union beta gamma, and similarly here gamma alpha union gamma beta. So, next let us move to the identities involving clean star or the star closure. So, many a times we will be having phi star. Okay. It is nothing but epsilon. So, phi means empty language, it is nothing but epsilon. Okay. And sigma epsilon star is nothing but epsilon. And suppose if you are having alpha star whole star is nothing but alpha star. So, because this is nothing but 0 or more number of times, so already we will be having, so this can be written as alpha star, and alpha star concatenated with alpha star is nothing but alpha star. And similarly how we have the subset concept under union, so here also we have it. If alpha star is a subset of beta star, then alpha star concatenated with beta star is beta star, because in beta star we have alpha star. Okay. So, this we can write like this, and we can do this in reverse way also. Here we have considered alpha star as subset of beta star, but you can consider beta star also as subset of alpha star, then alpha star beta star is alpha star. Okay. Why? Because beta star, it is a subset of alpha star. So, if you take the regular expression, so you will be having like this: A star followed by A union B whole star is nothing but A union B whole star, because A star, it is the language of A star, it is a subset of language of A union B whole star. That means for A star, so you can generate these strings from this expression. Similarly, so if you have alpha union beta whole star, it is alpha star beta star whole star. Okay. So, this union is there, so that you can take out with concatenation, and you can write like this, that is, if L of beta, it is a subset of L of alpha, then alpha union beta whole star is nothing but alpha star. For example, so if you have A union epsilon whole star is nothing but A star, because epsilon, it is a subset of L of A star. Okay. So, these identities, so we will be using in the simplification of regular expressions. Okay. So, let us move to the regular expression. So, that is, first let us consider A star union phi star union AA. So, this can be written as A star union phi means, so you can write it as A star, because phi is always a subset of L of A star. Okay. So, this again it can be simplified, and it can be written as A star union AA, and AA is always a subset of A star, hence further it can be simplified as A star. See, such a big regular expression we have simplified to A star. And similarly, here B union BB whole star, since BB will always be a subset of B star, so you can write B star followed by B star, which is nothing but only B star. So, because we have the closure identity as alpha star followed by alpha star is alpha star, and similarly A union B whole star followed with B star union. So, this can be simplified like this. Okay. So, A union B whole star, okay, followed with union of A B star, because B star, it is a subset of A union B, and that is why it can be written as, and similarly A B, it can generate from A union B. So, finally, it is simplified to A union B whole star. So, likewise, so these rules it can be used in many. Okay. So, likewise, here I have given A union B whole star followed with A union epsilon followed by B star. So, this is nothing but A union B whole star, because this is a subset of A union B whole star. Okay. So, in a similar way, phi star union B is nothing but, phi star is nothing but, we know that it is epsilon. Epsilon union B is nothing but, epsilon union B followed by B star is nothing but B star. Okay. So, because it is epsilon union B, it is a subset of B star, and similarly, so A union B whole star followed with A star means, so it can be written as A union B whole star, because you can generate the strings of A star under A union B whole star. So, that is why I have written here L of A star, it is a subset. Whenever it is a subset, so you can take either with union or with concatenation. This is nothing but L of B, L union A union B whole star, because you can generate the single B with A union B whole star. And similarly, whenever you have plus, again for that star is there. So, simply you can write star, because the outward will be having the prior importance, and so here it is 0 or more number of times repeated. So, always this will be a subset of this star. So, you can write A union B whole star. So, these are some of the identities which we have used and simplified. So, let us move to some of the exercise problems. Okay. So, in the textbook, So, the author has given many problems which I have found to be interesting. So, I have solved some and others I will be giving in my notes. Okay. So, here, so L is the language accepted by the finite state machine. Indicate for each of the following regular expression whether it correctly describes L. Okay. So, this is the finite state machine given. So, it accepts some language. So, what language it accepts? So, here some regular expressions are given. So, the author is asking, the question is whether these regular expressions they correctly define this language. So, let us test one by one. So, what is it? What is this? This is A union B A, either A or B A followed with B star A, B star A. It reaches the final state. Okay. So, but this is not the regular expression. Okay. So, whether the regular expressions correctly describes L, because this B star A, it can be repeated any number of times. So, that is why this is no, and here B star A, it is having whole star. So, that is why it is there. So, next, so likewise you can consider. So, this is the regular expression for the L of M. First it is A star union A star followed with B star, next followed with, that is A star B star A, next union followed with, so the same thing whole with AB followed with A union B star. So, likewise for any FSM you can write the regular expression. Okay. So, this is the FSM that describes the L of M, and we should find the complement. How to find the complement? So, for the given FSM, first construct the equivalent DFSM. So, we know how to construct the DFSM and then complement the DFSM. How to complement the DFSM? Change the non-final states as final states and final states as non-final states. So, for this example, so if you consider for example this problem, okay. So, the previous also can be found out the same way. Here I described the method. So, if you complement, if you find the DFSM, so it will be having these states. In all the states Q0 and Q2 are present. So, if you want to complement it, there are no final states. Okay. So, all these final states are there, there are no non-final. So, the write the regular expression that describes the complement is, since there are no states, so you can write as phi. Okay. So, because so Q0 and Q2 are present in all the states. So, you cannot make other than this. So, L of M will be phi. And similarly, so we know that A power n, B power n. So, if n is not specified the limits, then it is not a regular language. When n is having the limits from 0 to 4, either epsilon, AB, AA, BB. So, you can construct the FSM like this. Okay. So, with epsilon, then AB followed with AA, BB, then followed with 3A's, 3B's and followed with 4A's, 4 this. Okay. Suppose if it is a generalized n greater than 0, then it is not a regular language, then you cannot construct a finite state machine, but you can construct a push down automata. This further will be taking up. So, these are some of the important problems I am discussing. So, this is the NFSM from the regular expression. Okay. So, in the previous we have constructed the DFSM. This is the NFSM, which consists of B, A, okay, or it is A union B B. Okay. So, A union B B followed with A star B, followed A union B B followed with A star B, or also it can be B A. So, there are two accepting states, either 3 or 6. This is the simple NFSM. So, likewise, so you can construct the DFSM. This is A B, A B whole star, it can be repeated any number of times, followed with AAB, it reaches the final state, and this AAB, it can be repeated any number of times. Okay. So, this is the DFSM. All others you can give to the trap or the dead state. Okay. So, this is the simple regular expression. So, till now we have discussed the how to write the regular expressions for the complicated cases, and then how to build the DFSM, and we have discussed the applications and simplifying the regular expressions, and we have discussed some of the exercise problems. Okay. So, this completes the regular expressions. Next, in further, so we will be moving to the regular grammars. In tomorrow's class, in the next lecture, so we can see what is the regular grammar, and then we will be continuing with that. So, for any of your queries, so you can reach me to the displayed mail ID. Thank you one and all.